Hello. I have a new set of interview questions to go through today. I have managed to look at some of them, not all of them, and I thought about some of them. I'm not sure about my answers for all of them, but this is kind of my progress. So I'm gonna start with the first question, which is a very nice um, graph sketching question, and I have seen something similar before it, so I kind of know what to do. So notice that I can rewrite this in this way, where I have a difference of two cubes on my left hand side and a normal x minus y on the other. Now, if I expand out the difference of the two cubes, I get the following. If I remember it right, at least. Now, this is very important because if I rearrange this in this way, I can say that part of my graph is going to include the line x equals to y. Therefore, if I make my sketch here, I think that's a good space. This is going to be part of my sketch. Now notice I can name a few trivial points that I know that are going to be here. If you factorize this out in this way, because if you factorize 1x out, you're going to have a difference of two squares, and the same with the y's. So these are kind of my points. The origin goes, this goes, this works, this works, this also works, and I'm missing a few. Does these two work? Minus 1 cubed is minus 1, minus 1 is plus 1, and 0, 0. That works. Therefore, by symmetry, this also works. 1 minus 1, 0. Yes, so all of these work. Now, I know that my graph is going to have um, 0 minus 1. I'm going to say it's here. And 1 here. It also is going to have 1 and 0. I mean on the y-axis, so this is 1 and minus 1. Okay, but I don't know yet what's this going to look like in the middle. So now all I have left is to analyze this term in the middle. Now this is part of the family of uh, conic shapes or conic sections. And to check what kind of shape this is, I will check the determinant of it. So in this case, the determinant is going to be 1 minus 1 minus 1. Nope, that's incorrect. The general formula for a conic section is the following. No, scrap that. You can think of this. I'm gonna write it down here. If I set y equal to 0, I get x squared minus 1. That means x goes to plus minus 1, but we already knew that. And therefore, by symmetry, it's also going to go through plus minus 1. I'm quite sure this is the shape of an ellipse, because if I check this determinant, it should be minus 3. And I know that if the determinant is negative, it's going to be an ellipse. If it's positive, it should be a hyperbola. So if you think of a cone this way, hopefully my drawing is not awful. If I have a plane and I cut through like this, as in like cut through like this, the shape I'll be making, or at least the cut, is going to be this. Now, if I tilt um, this this plane that's cutting through, I will get something like this, and my cut is going to be something like this. And depending on how my tilt is, I'm either gonna get a hyperbola or a parabola or an ellipse or even a circle. These are all the possible kind of shapes I can kind of get from conic sections. And I think it's important to recognize that this is an ellipse. And it's going to be a special ellipse because the xy term is telling me that it's tilted slightly. And first of all, I can kind of check where um, where my ellipse is going to intersect the x-axis, because I know that is symmetrical on the line y equals to x. I'm gonna substitute in that into the ellipse, and it's going to look like something like this. Um, which is roughly, let's say, here, and by symmetry is also going to be here. Well, one of root 3 is bigger than 1, so this is going to be here. So it's definitely not a circle. And if you have a ellipse, the squished sides kind of tell you which one is the elongated side. So I know my elongated side is going to lie on this axis. So if I check like trivial points, like let's say -1, -1 and 1, which I think I have put here. No, I haven't. -1 and 1 are actually points that do work. So these points here do work. And from here, I can kind of trace out the shape of the ellipse. This is perhaps not my best sketch. Luckily, this is a sketch and not an exact plot. But this is kind of the graph you would get. I do think I should learn and revise how to do conic sections or recognize them or look deeper into them, because this is a very interesting graph. I've seen a similar question, but much easier one, in my opinion, because I know how to do it. And it was something along the lines of x squared, I think it was minus y is equal to y squared minus x. Something along the lines of that. I'm not going to do it. I'm not going to do that now, but because I have more questions to do. So now, my next two questions, I'm kind of going to do them together. Show that cos 2 pi over 7 plus cos 4 pi over 7 plus cos 6 pi over 7 is equal to minus a half, and prove that for every odd integer, this statement here holds. The way I thought about this is using further maths content, A-level further maths content, roots of unities, and like C plus IS. So I know something important, that this is the real part of the seventh root of this equation. Let's say that's written wrong. It should be a 7. Z is a complex number raised to the 7, which is equal to 1. And I'm gonna say the roots of this equation is I 1, because of course 1 to the 7 is 1. W or actually omega squared, omega cubed, omega to the 4, omega to the 5, and omega to the 6. These are all my roots. Now I know that 1 is also equal to, in the Euler form, e to the 2 pi I, or 2 pi I k for like all integer values of k. So I can say that w is equal to e to the 2 pi over 7I. W squared is 4 pi 7I. Okay, nice. I also know that the real part, so what I'm being asked, is equal to the real part of e to the 2 pi over 7I plus e to the 2 pi 4 pi 7I plus e to the 6 pi over 7I. This is kind of what I'm being asked. Now, this is a geometric sequence, which I will get to in a second. But one thing to note is that this, I can use a technique within the roots of polynomials, that I know that the sum of the roots is going to be something that I can work out by looking at this expression here. The sum of my roots is going to be 0. And that's because if I rearrange this, z to the 7 minus 1 equals 0, my, let's say, a z to the 6 term has coefficient 0. And we know that minus b over a is the sum of the roots, which is in this case 1 plus w squared plus w cubed plus w to the 4 plus w to the 5 plus w to the 6. There is one other fact I will have to like bank on for this, what I'm about to do to work, is that this, which is my initial sequence, which actually should give a name to it. I'm gonna call this t. Has conjugates being these parts of the sequence. So w, its conjugate is w to the 4. And you can kind of see that because 2 pi of 7, if you look at the arguments, and you do 2 pi minus 2 pi by 7, I think that's correct, you get 12 pi over 7. Or actually, this is the conjugate of that. So, because my omega to the 6 is 12 pi over 7. So, when I write this, theta plus I sine theta, the conjugate of this is cos theta minus I sine theta. Notice how my real part isn't affected. So, I put piecing together all this information. I'm going to rewrite this as 1 plus w squared, w cubed, w to the 5, and w to the 6, and I believe I missed w to the 4, doesn't matter, is equal to 0. I'm going to bring the 1 to the other side, and I'm going to call this t, or at least the real part of t, because that's what I'm concerned about. I'll get to that in a second. T plus w to the 5 w to the 6, w to the 4 is equal to minus 1. Now, I know that the real part of this 4 is minus 1. Now, I know that the conjugate, in this case, the real part doesn't get affected. So actually, this is just t. R2t is equal to minus 1, which means 2t is minus 1 because minus 1 is a real number. Therefore, t, our original uh, sum, is minus a half. Hence, we've shown this. Now, the beauty of doing something like this is that we basically did the question 3 as well, because I can extend this argument for any n odd n, and this would also work. I haven't actually thought why this wouldn't work for an even n, and I guess it's because you are not going to get quite the same formation, because in this case we can match all of the conjugates, but let's say for a z to the 4, let's say you have 1 w squared and w cubed. You don't exactly have all the conjugates you need. This trick works because the real part, when it comes to complex numbers, the conjugate of real part doesn't get affected, but the imagined part does. But we're not concerned with imagined parts, we're concerned with real parts. This is kind of how I would do these two questions. Now, moving on to the next question, I believe my pace is a record. I've done 3 questions in 17 minutes. I mean, to be fair, I have kind of looked at them and you know had my preliminary views about them before when I was in school. But yeah, this question gave me a headache because it's there's like so many red herrings to it. I was thinking of like difference of two squares that doesn't take you anywhere, and the way I realized that this is perhaps not the most intuitive graph is that it only exists between a certain specific domain, which I need to specify. Now, the first thing to note is that the graph of ln x squared is something like this. So again, it doesn't exist on negative x values. So this is in the normal ln x graph, which has asymptote at the y-axis. Now, the ln x squared, I believe, looks something like this. Okay. Now, the graph of x to the 4 looks something like this. Because we're not concerned about the negative x-axis, I'm only going to draw it on the first quadrant. And this is kind of how it looks like. Now, notice how if I have y squared being equal to ln x squared minus x to the 4, and I rearrange this in this way, whatever is under my square root must be positive. This implies that ln squared x must be greater or equal to x to the 4, which means that the absolute value of ln x must be greater or equal to x squared, which is very interesting because if I look at this, how do I draw this? Maybe like this? I don't know. I don't exactly know how can I draw this. Does it intersect? I think it does. I'm not sure. I haven't used Desmos to actually check my answers. But yeah, I mean the point I'm making is that ln x must be the modulus of at least must be greater than x squared. Oh yes, yeah, actually. This is 1. Okay, yeah. But bear in mind we're talking about Linux squared, in my original graph. Actually, it is better to think about this in terms of len squared and x to the 4, because then my graph looks slightly different. Yeah. So the range that we're interested in is this. Yeah, and this is very important. I still don't know what this point is, and I am under the belief that I cannot work this analytically, or at least I have to use a numerical method to do so. And in an interview is quite hard to. That's why to work to work it out. That's why I think this question is a bit evil, unless there is a trick I'm completely missing, which I am probably missing because I'm quite mediocre when it comes to these questions or maths overall. But yeah, so this is where my graph is going to be, the domain of it at least. Now I know it can't be 0, as in like it's my actual graph is going to approach from infinity. So if I mean I don't know why I changed color of pen, but as you can see, there's an asymptote, and how can I actually show this? When x equal to 0, um, okay, yeah. So I am looking at the range between 0, x, and let's say x naught, which is less than 1. X naught being this point here, which I should define. Now, I know the behavior of x between in the graph of len x squared here uh, is the same as, because if you have a fraction, let's say, actually it's better if I write it this way, x is equal to 1 over alpha, where alpha is an integer or rational number less than 1, sorry, more than 1, then I can rewrite this as this, which means I can write as this, which means I can write this as this. It's going to be a positive number, very large one, or kind of, yeah. You get the point. You get the point if you get the point. So that means I am technically looking at this part of my graph, not even here. When it comes to strictly length squared alpha or length squared x. So, um, how can I say this? My graph is going to look something like this, where this is my x naught, which is my maximum point. And now, if you notice, if I substitute, minus y, I get minus y squared is equal to ln x squared minus x to the 4, which is the same exact thing. What this implies is that my graph is actually has a symmetry in the x-axis. So if I know what happens above the x-axis, I know automatically what happens below the x-axis. So I can determine this, that this is how my graph is going to continue to look. I don't know why it's not loading, but this is what I drew. For some reason it doesn't show. It's not showing in the Miro board. Let me refresh. Please work. Please work. I am 25 minutes in, so progress is not bad. And I've noticed most of my videos like an hour long. So me actually kind of looking at the questions beforehand and only leaving a few that I haven't actually done is quite helpful. Otherwise, it's torturous to anyone watching this. Why it's why it's Miro is acting up. I mean, I can try and show it in my webcam. This is kind of how my graph is going to look like. And the reason I say that it's going to approach x naught is I can take limits. And I'm going to show that in a second when my Miro board loads. Because I can justify this if it just loads, which is seems it's not. Let me open my different tab. Perhaps it will work then. It's not working. It's not working. Please work. In worst case scenario, I just use paint. It's very stupid because my the sensibility of my mouse is insane, and I doubt OBS is capturing it. Okay, is that can that be seen? No, my OBS is bugging out. I think I may have to end the video here because it's not seems to be not working. See if we can fix this. Uh, well, sadly not. I will have to end sadly the recording here. Seems to me Mire is not working. Ah, what a shame. I was really enjoying doing this. Why when things okay, I'm just gonna end this.